So we stopped with this in the last class. We actually had to find out the electric field at point A, B and C, and there are two plates given. One is positively charged and second one is negatively charged. Okay, so if we have that, no issues, let's do it. Okay, no problem. It's a normal problem, electric field. Let's do it anyway. Okay, so we have uh, to find out what is the electric field at these 3 points. Okay, this is actually a bit logical. The first thing we have to understand that whenever we are talking about a positive charge or a positively charged plate, the electric field will be away from the plate. If it's negative, it will be towards the plate. Okay, so let's say I have got these two plates, and if I want to find out the electric field at this point B, it will be because of this negative plate as well as because of the positive plate. We cannot ignore the positive plate because negative plate is closer, because that also depends, okay, affects the electric field. So for the negative plate, let's mark this as 1. Let's say this is my plate 1 and this is my plate 2. Now at this particular point, because of plate 1, the field will be away, we know, because it's positive. E1, please make sure that this is clear. E1, because this is because of the positive plate, the field will go away, and because of E2, the field will be in this direction, E2, because it's negative. So that's the reason. Okay, and the electric field is a vector quantity. Similarly, you check here, because of this positive plate, the field will be in this direction, and because of the negative plate, the field will be in this direction. So they are opposite, right? Let's check for point A. If we check for point A, because of this positive, the field will be away from the positive plate, and because of, so this is my E1, and because of the negative plate, the field will be towards the negative plate, so this is E2. So this is the main diagram or main understanding that we need to have. Now let's see what is E1 and E2. So we have already done it in the last class, that if you want to find out the electric field at any point P at a distance x from a plate, answer is sigma by 2 epsilon naught. Okay, depending on whether it's positive or negative, only the direction of the field will change, but the magnitude will remain the same. Okay, and it does not depend on the distance from the plate. So that means in this case, both E1 and E2, this is the trick here, is sigma by 2 epsilon naught. Both will be same because it does not depend on the distance. That is something which we have already concluded. So both will be same. Okay, therefore electric field at B is E2 minus E1 because they are in opposite direction and both are equal. So this is nothing but 0. Same is the case for electric field at C. But when we consider the electric field at A, this is nothing but E1 and E2 are in the same direction. So I can write it down as E1 plus E2. So this would be 2 times of sigma by 2 epsilon naught, which is sigma by epsilon naught. So if we are having one plate, positive negative, the field is this. If we have two plates and we want to find out what is the field in between these two plates, the answer would be sigma by epsilon naught. So in electric potential, the interesting part is, or you can say it's the friendly part of study, it's a scalar, it's not a vector. So resolving a vector or looking into the direction and all, that is actually out of the electric potential scope. In electric potential, you don't need to know the direction, you just need to know the magnitude because it's a scalar quantity. In that way, the calculation becomes very easy. Okay, so the idea of potential at a point is actually not true. Okay, you can say potential difference. The potential difference has got a very important meaning, and from potential difference we can find out what is the potential at a point. Okay, so electric potential, I think we should start with this idea of what is potential difference. Okay, and I hope you understand what is potential. It is the same English dictionary meaning. Like someone in the class has got great potential to score well in exam. Okay, or someone has got great potential to be a sports person, right? So that's the idea of potential. Okay, Similarly here also, if you are basically having a charge and if you want to know that how much effect it is going to create in the surrounding, it will depend on how much potential it has. Okay, that means if I want to bring a charge from one point to another, okay, let's say I have got a charge at this particular point, let's say this is point B, and I have placed a test charge Q naught here. This may be a positive test charge. Okay, maybe I can write it down just as test charge. Okay, and I want to take this charge from the point B to point A. Okay, so near this point A might be there is another charge, but even if you don't consider that, if you want to take this charge from point B to point A, I have to do some work. Okay, so doing that work and connecting it with potential is very important to understand the concept. Okay, so what we say here is the potential difference. So let's say the potential here is B and the potential here is VA. So that means now if I want to write down what is the potential difference, I will simply write it down as VA minus VB, right? That's my potential difference. That means by definition it means how much work is done. Okay, so I will write down this as how much work is done, but that is actually nothing but called as the external work. You might have a charge here, it might be positive. If you want to take it from here to here, that will actually repel. So you want to do that work against this force. Okay, so how much external work is done in order to take the charge from B to A. Okay, this is very important. This is the idea, divided by Q naught. We can write it down that way. Okay, so how much work is done per unit charge in order to move it from B to A is actually the definition of potential difference. Okay, this is potential difference. If this idea is clear, we can easily define what is potential. Even we are going to prove it also. That's very important. Okay, so this is my potential difference, but I need to find out what is my potential also. Okay, potential at a particular point. So this is called as the potential difference, and this is these are important to remember. This is a scalar quantity, and of course the unit is work done, unit is joule, and charge, the unit is coulomb. So joule per coulomb is the unit. So this is the idea behind potential, but we can also find out what is the potential at a point. Potential at a point. Now let's look into the idea of potential at a point from simply looking into the different definition of potential difference. Look here, this is the potential at A, this is the potential at B. If either of them becomes zero, maybe VB, if I can make it zero, I can say what is the potential at A. Okay, if I can make VB 0, I can say what is the potential of A, because VA minus 0 it will be. So that way I can define what is the potential at that point. Now imagine you have a charge here, and let's say let me take this is my charge here at point A, or maybe this is a point here, and I have got another point B, but this time this point B is at infinity, it is at a very far distance. Okay, so if the charge is at a very far distance, that means the potential at infinity will be very close to zero, so we can approximate it to be zero. So this potential of Q naught at a very far distance with respect to A is zero. Okay, so I need to do some work in order to bring this charge from B to A. Okay, so if I go by this definition of potential difference, okay, the thing is, first thing we have to imagine that let this B, which is the point at which the charge is kept, is at infinity. It's at a very far distance. That means we are going to find out the potential difference as VA minus V infinity. So this is nothing but the external work done in order to bring a charge from infinity to A. divided by Q naught. So if you go by the bookish definition, the definition of potential is V infinity sorry infinity is 0. As I said, the potential at infinity will be 0, so I can write it down as VA is equal to W external in bringing a charge from infinity to A, okay, and that charge is Q naught. This is the definition of potential. A very interesting idea, and if we just look into this definition, and if you check your book, whatever definition is being given can be in any book, Griffith and all, you can check. Okay, you'll see that the definition is, it is the work done in per unit charge to bring it from infinity to a point. That is the definition of potential. And what is potential difference? It is the work done per unit charge to bring that charge from a point B to point A. So even if you don't recall the definition, no problem, just remember this expression and you can easily write down what is the idea of potential difference and potential. Okay, let's write down some important notes which we have to take. Okay, this work done that we are considering, always remember, is external. Okay, so work done external should be considered. So that means if there is a force here, we're doing that work against that force, so that's the external work done. That is very important. And of course we also know that work done is path independent. It does not depend on the path. So sorry, independent, very important. So we have to remember these two concepts whenever we're talking about the potential and this. Okay, now let's see the formula for potential, okay, due to a point charge. Okay, so this is the work done definition we have seen and we are going to use it. Okay, so our next topic is electric potential. Okay, we have to find it out at a point. Okay, at a point, okay, due to point charge Q. So remember, we are considering a point charge, and what is the electric field potential because of that point charge is something which we want to calculate or we want to find out. Okay, so that's our topic here. Important. So let's try doing this. Actually, what we have to prove here is this: Vp is equal to Kq by R. Okay, so that will be the potential. Let me write it down as capital Q. So it is Kq divided by R. This is something which we have to show. The question is how. It is very closely related to electric field. If you remember, electric field was nothing but Kq by R square. We have checked it also. Here we have to show why potential is Kq divided by R. For this, what we are going to do is we are going to consider a scenario. The scenario is something like this: I have a point P, okay, and I have the charge Q here, and let's say the distance between this Q charge and the point P where I want to find out the potential is R. This distance is R. Okay, so the question is, what is the potential at P due to charge Q placed at a distance R? Okay, so what we are going to start with is the definition of work done. So work done definition, it says, or the potential definition, it says that I have got a small test charge Q naught. Test charge means it does not have a field of its own and it's a positive test charge. It is at infinity. Now I will do some work in order to bring this test charge from this point to the point P. And as soon as I bring it on this at this particular point, I will see that the displacement will be in this direction, dr, but I'm applying a work done. That means I'm doing the work done against the force, okay, and that work done is in this direction. So this is the external direction of the external force. I'm using an external force and trying to bring it in this direction, but the displacement will be in the opposite direction because this is positive and this is also positive. Okay, so we can just write down what is the force. So force on Q naught when transferred from infinity to P. So I'm bringing it from a very far distance to P. So force we already know, K, first charge was our Q, the test charge is Q naught divided by R square, right? If you know the force, we can find out work done, because force, work done is equal to force into displacement. So we can do that. So we're going to use that definition. And work done per unit test charge is nothing but the potential. So we're going to use that definition. But now what we are going to do is we are going to find out the work done. So let's do it now. Work done, okay. We are actually doing a work in order to bring that charge, okay. Now you can, you can bring it from infinity to point P, or you can take it from P to infinity. Both will be the same but opposite in direction. So it's a conservative system. So whatever is work done in taking the charge from P to infinity, same would be the work done in bringing the charge from infinity to P. So let's say I'm talking about the work done in order to take the charge from P to infinity. Okay, so that is my limit. So I know work done is equal to force into displacement. Let's say the small displacement is dr. I'm finding out the total work done, so I'll go from P to infinity. P means the distance from the charge Q is r, so I should not write down P here. The distance is in r. I'm taking it from r to infinity. Okay, that's the idea. So here we can replace this. So we can write it down as r to infinity. This is a dot product. Obviously, work done is force dot displacement. Work done is a scalar, but force dot displacement, both are vectors. So this would be f dr, but f is in this direction, dr is in this direction. So that means we can write it down as cos of 180 degree, and cos of 180 degree is nothing but -1. So I can take it as minus integration r to infinity f dr. Now if you look into this force, we can see minus k, q, q naught are constants, they don't change. Q, q naught are constants, and I can integrate it minus r to infinity into dr, but there is the r here, so I will take it by r square. So that means we have to just integrate this. So we can integrate this minus of k q into small q naught integration 1 by r square, so that is nx to the power n minus 1. Okay, so uh, we can just do it that way, simple. So it is integration, so x to the power n plus 1 divided by n plus 1. So if you do it, 1 divided by r, and the limit is from r to infinity, right? So it is minus of k q q naught within bracket upper limit minus, we can in fact take the minus sign out, so it will become plus. Okay, don't need it. So you can simply write it down as upper limit 1 by infinity minus of 1 divided by r. So 1 by infinity is 0. 0 minus 1 by r is minus 1 by r. So that means I'll get it to be minus of kq q naught divided by r. This is the work done. But what is the definition of potential? Potential says that, okay, v, I can talk about this. Potential is equal to W external in order to take it from infinity to P divided by Q naught, right? So this was W from P to infinity, okay. Talking about conservative force, W from infinity to P would be nothing but same, but it would be plus, okay. K Q Q naught divided by R, right? So we can just replace it here. So we can simply write down that the potential is, let's take this kq q naught by r divided by q naught. Let's cancel this out. We're getting it to be r. Okay, so that's the proof for this. This proof comes from the definition of potential difference and potential and the idea of work done and potential connection.